Hello, my name is Meysam. I'm second year PhD student working on visible light communication under supervision of Professor Valeria Loscri with Inria, Lille-Nord, Europe in France. I'm going to talk about adaptive link protocol for visible light communication. This presentation includes introduction, short definition about vehicular and visible light communication. Then we're going to move to the main part where I explain our system model. Afterward, system model will be validated with some results and interpretation. Finally, I conclude with summary of the paper, and if the time allows, I'm going to talk about the next steps in my thesis. Two main motivations of this work are a lack of scientific attention to outdoor application of visible light communication in the strong background of vehicular communication to host VLC. As you see in the bar chart, the portion of research made in outdoor application VLC is tiny since 2010, which comes contradictory to the fact that vehicular communication can host VLC. With widespread LEDs and cameras on the cars and roadside units, vehicular communication seems to have the base to use VLC. Moreover, VLC is commercially more convenient than radio frequency equipment. For example, thanks to the intensity modulation and direct detection mechanism, local oscillator has been excluded from the receiver block. Here comes the question. If visible light communication is a sophisticated technology to be adopted in cars, why it is not yet been well implemented? Actually, VLC face two major challenges in vehicular communication, which are connectivity and mobility. VLC has a short coverage due to line of sight constraint, which should maintain in the dynamic vehicular scenario. Our contribution in this paper is defining medium access control protocol dedicated to vehicular visible light communication by defining a realistic channel model and increase the connectivity and the data rate upon the channel. What is VLC? Visible light communication is a subset of optical wireless communication falls between ultraviolet and infrared. It has been suggested as a complement to radio frequency technologies which support illumination and transfer data at the same time. VLC system made of transmitter, free space, optical link, and more complex receiver. On the other hand, vehicular communication aims to increase the transportation safety and experience in vehicular-to-vehicular and vehicular-to-infrastructure scenarios. Our system model made of channel model, noise model, and the protocol model. Channel model is a duplication of Lambertian emission model, which mainly consider the path loss and the climate distortion, which takes into account weather impacts on the signal. Probability density function of the climate distortion with sigma L square as a log normal variance estimated by ray tracing analysis. Main elements of the noise model are thermal noise and the shot noise. You see, the shot noise variance is a function of the background power hits the photodiode area and depends on the ambient illumination ranges in the upright table. Table in the bottom shows the terms and the parameters used in the system model. Link adaptive protocol starts with broadcasting a tiny control message named pilot in the transmitter. Photodiode sweep the optical link every pilot time slot and measure the received power and consequently signal to noise ratio as in the equation. If the SNR measured is more than the minimum amount considered as alpha, then it passes to the association step. Otherwise, it scans the link again. At the association level, the transmitter unicast association request to the source of approved SNR, and if the request accepted, transmission starts. If not, it goes back to scanning phase. Transmission starts with the lower modulation level and depends on the evolution of the link quality. The data rate changes according to the modulation table. Once the SNR per bit falls below the threshold alpha, photodiode restarts searching for alternative link and handover. To assess the functionality of link adaptive protocol, we suggest outage probability and good put metrics. I'm going to talk about this later on. Generic scenario in the figure arranged in order to include association, adaptive modulation, and handover phases using NS3 simulator. NS3 VLC module is made upon point-to-point net device and point-to-point channel by adding VLC classes such as VLC net device transmit, received, and VLC channel. You can find more details about this module on GitHub link. I put it here. In the scenario, node 1 traveled for 20 meters in 10 meters per second velocity, passing by node 2 and node 3. During this journey, node 1 measured the link quality and associate to the node 2. Adapt is modulation to the SNR, and in some point between node 2 and node 3, SNR from node 2 falls below the threshold, which has set to 11.5 dB to comply with the maximum error probability required for safety application in transportation. Simultaneously, SNR from node 3 surpasses the alpha, so node 1 connects to node 3 and repeats the earlier steps. In order to evaluate the connectivity of the link adaptive protocol, we define outage probability as a probability that the signal quality falls below the threshold at the cell edge. SNR can be translated into distance, so the outage probability will be like probability of the distance between transmitter and the receiver when it's bigger than the receiver coverage Dmax. If we fix the outage probability to 20%, which means 80% of the time nodes going to stay in the VLC coverage, our model has a higher coverage along with slotted aloha using OOK up to 3 meters, and it outperformed the slotted aloha with VPPM and 16 QAM and also 16 PSK modulation. For the data rate assessment, let's look at the good put as a function of signal to noise ratio for different modulations. Slotted aloha keeps a constant good put when SNR overpasses the threshold, while LAP adapts the data rate and as a result the good put to the best of the link quality. You see in the figure left bottom, the link adaptive protocol good put reached higher good put when SNR increased. The amount of delivered data traffic depends not only to the SNR, but also to the pilot rate. As it's visible in the figure in the right, higher pilot frequency results in higher amount of delivered data traffic compared to the ideal case. Because when we increase the pilot frequency, in fact, we increase the system awareness, and we can trace the change in the signal strength immediately and adapt the data rate to the link quality. The figure in the bottom left proves that this augmentation in data rate happens in different speeds. It's true that increasing pilot frequency increases the system awareness and the data rate, but at the same time, it imposes more overhead to the network, which is redundant to the data traffic and reduces the protocol efficiency. You may see the generated overhead increase as a pilot rate increase, which means the protocol efficiency degrades. Finally, we introduce a MAC solution dedicated to the vehicular visible light communication. It includes realistic channel model of Lambertian path loss and climate distortion. Link adaptive protocol has a 3 main contributions: tactile scanning, single handshake association, and adaptive modulation scheme. We validate our model by showing some results in terms of outage probability and good put rather than further discussion on protocol efficiency assessment. As a result, a trade-off is required between protocol efficiency and pilot frequency. Okay, I'm gonna skip this slide. And yes, thank you for your attention.